Welcome! In this session, we will explore problem number 927, titled 3 Equal Parts. This problem challenges us to divide a binary array into 3 equal parts with specific constraints. We'll analyze the problem, consider different approaches, and break it down step by step. Let's dive in. The problem asks us to split a binary array ARR into 3 non-empty parts, where each part represents the same binary value. To do this, we need to identify two indices, I and j, such that the array can be divided into 3 segments. The first segment consists of elements from the start of the array up to I, the second segment begins immediately after I and ends at j, and the third segment contains all elements starting just after j until the end of the array. Importantly, each of these segments, when interpreted as binary numbers, must have the same value. Leading zeros are allowed in any of the parts. If splitting the array in this way is not possible, the output should be -1, -1. Let's explore some examples to better understand the problem. In the first example, the input array is 1, 0, 1, 0, 1. One valid solution is to split the array as follows. The first part is 1, the second part is 0, 1, and the third part is 1. Each of these parts, when interpreted as binary numbers, equals 1. Therefore, the output is 0, 3, representing the indices that divide the array into these 3 parts. However, in the second example, with the input 1, 1, 0, 1, 1, there is no way to divide the array into 3 parts such that all parts represent the same binary value. As a result, the output is -1, -1. Finally, consider the third example, where the input is 0, 0, 0, 0, 0. Here, the array consists entirely of zeros, and the binary value of all parts is 0. A valid split would be to divide the array into 0, 0, 0, and 0, 0. These 3 parts all have the binary value 0, so the output is 0, 2, indicating the indices that separate the array into these segments. The problem also comes with certain constraints. The length of the array is guaranteed to be at least 3 and at most 100,000. And every element in the array is either 0 or 1. Additionally, binary values are determined by concatenating all bits in a part, and leading zeros are acceptable. These constraints emphasize the need for an efficient solution that can handle large inputs while adhering to the rules of binary representation. When tackling the problem of dividing the binary array into 3 equal parts, one intuitive approach is the brute force method. Here, we iterate through all possible pairs of indices, denoted as I and j, to split the array into 3 segments, the first from the start to index I, the second from I plus 1 to j, and the third from j plus 1 to the end. For each pair, we convert these segments from binary to integers and compare their values. However, this approach quickly becomes computationally infeasible. With each split, we perform multiple operations like slicing, converting, and comparing, leading to a time complexity of n cubed. This is far too slow for larger inputs, making the brute force solution impractical. To address this, we turn to a more efficient approach, grounded in the structure of binary arrays. A crucial observation is that for the array to be divided into 3 equal parts, each part must contain the same number of ones. If the total number of ones in the array is not divisible by 3, it's impossible to find a valid solution, and we can terminate early. This insight forms the basis of the optimized approach. Now, once we've established that dividing the array into 3 equal parts is feasible, the next step is to pinpoint where these divisions should occur. The target number of ones in each part is calculated as the total number of ones divided by 3. With this target in mind, we locate the starting positions of the first, second, and third sections of the array by identifying the indices corresponding to the first, second, and third groups of target _ones. After determining these partition points, we need to verify that the binary values of the 3 parts are identical. This involves ensuring that when any trailing zeros are aligned, the segments match exactly. By narrowing our focus to these specific partition points and aligning the segments, we can confirm whether the array can indeed be split into 3 equal parts. This strategic approach eliminates the inefficiencies of the brute force method and significantly speeds up the process. The optimized approach is chosen because it transforms the problem into a linear scan, making it highly efficient. With a time complexity of n, it avoids the computational overhead of the brute force method, which operates at n cubed. It's also space efficient, requiring no additional data structures and maintaining a space complexity of 1. The key insight driving this solution is that for the binary values to be equal, each part must contain the same number of ones. Recognizing this allowed us to simplify the problem dramatically. Locating the partition points based on the positions of the first, second, and third groups of target_ones was a pivotal realization that shaped the final design. While the brute force method is straightforward to implement, it's unsuitable for large inputs due to its inefficiency. On the other hand, the optimized approach is not only faster but also scalable and robust, making it the clear choice for this problem. The goal of this problem is to partition a binary array into 3 contiguous segments such that the binary value represented by each segment is identical. If this cannot be achieved, we need to return an indication of failure. To start, the algorithm first validates the input. We calculate the total number of 1s in the array, referred to as total_ones. Here's a key insight: if total_ones is not divisible by 3, it's impossible to split the array into 3 equal binary segments, so we immediately return failure, such as -1, -1. On the other hand, if total_ones is divisible by 3, we compute the target number of 1s that should appear in each segment. This value is simply ones_per_segment equals total_ones/3. Additionally, if the array contains no 1s, meaning it consists only of 0s, then any split is valid since each segment will have the same value of 0. In that case, we can return an arbitrary valid result. Once we know the target number of 1s per segment, we proceed to locate the key indices in the array. This involves identifying the starting positions of the 3 segments that potentially form the solution. Specifically, we determine the index of the first one in the first segment, the ones_per_segment plus 1, th1 for the second segment, and the 2*ones_per_segment plus 1, th1 for the third segment. These indices are referred to as first_start, second_start, and third_start. After identifying these indices, we verify if the segments starting at these positions are equivalent. This step involves sliding through the array simultaneously from these indices and comparing the binary values in each segment. If the segments differ in any way either in length or content, we return failure, denoted as -1, -1. However, if the segments are identical, we compute the partition points. The end of the first segment is given by partition 1 equals second_start 1, and the end of the second segment is partition 2 equals third_start 1. Finally, we return these partition indices as the result. At the heart of this problem lies the insight that the total number of 1s must be evenly divisible by 3. This ensures that each segment has the potential to represent the same binary value. Additionally, instead of converting binary values to integers for comparison, which could be computationally expensive, we use a sliding comparison approach. By comparing the segments directly from their starting indices, we can efficiently verify their equivalence. It's also important to handle edge cases carefully. For instance, if the array consists entirely of 0s, any split is valid. If total_ones is not divisible by 3, no solution is possible. And if the segments differ in length or content during the comparison, we must return failure. The only data structures we use are the input array itself and a list to store the indices of 1s in the array, which helps us quickly locate the starting points of the segments. The time complexity of this algorithm is O(n), where n is the length of the array. This accounts for traversing the array to count the 1s, locating the key indices, and comparing the segments. The space complexity is also O(n), primarily for storing the indices of 1s. Let's walk through an example to solidify our understanding. Consider the input ARR equals 1, 0, 1, 0, 1. First, we count the total 1s, which is 3. Since 3 is divisible by 3, each segment should contain 1 1. The key indices are first_start equals 0, second_start equals 2, and third_start equals 4. Comparing the segments starting at these indices, we find that 1, 1, and 1 are identical. The partition indices are computed as partition 1 equals 1 and partition 2 equals 3, so the output is 1, 3. For edge cases, consider ARR equals 0, 0, 0, 0. Any valid split, such as 0, 1, is acceptable. For ARR equals 1, 1, 1, the result is 0, 1. Finally, for ARR equals 1, 0, 0, 1, 0, 0, 1, a valid split would be 2, 4. Here we start by defining a class called solution, which contains our main method, 3 equal parts. The first step in this method is to calculate the total number of ones in the given binary array using the sum function. This total count is crucial because it determines whether it's even possible to split the array into 3 equal parts. If the number of ones is not divisible by 3, we return -1, -1, indicating that dividing the array into 3 equal parts is impossible. Similarly, if there are number ones in the array, then the array can naturally be split into any 3 valid parts, so we return 0, len, r, 1, representing the entire array as the valid range. Next, we calculate how many ones should be in each part by dividing the total number of ones by 3. This value, stored in ones _per_ part, helps us determine the indices where each segment of the array should start. Then, we initialize variables to store the starting indices of the first, second, and third parts, as well as a counter to keep track of how many ones we've encountered so far. As we iterate over the array, whenever we encounter a 1, we increment the count and assign the first, second, and third indices accordingly. These indices mark the first occurrence of a 1 in each of the 3 parts based on the ones _per_ part calculation. Once we have determined the starting indices for the 3 parts, the next step is to ensure that the binary patterns starting from these indices are identical. We use a while loop to compare the elements at the first, second, and third indices simultaneously. As long as the values at these indices are equal and the third pointer has not reached the end of the array, we increment all 3 pointers to continue the comparison. If the third pointer reaches the end of the array while this condition holds true, it means the parts have identical binary patterns, and we can return the indices for splitting. Specifically, we return first, 1 and second as the indices where the array can be divided into 3 equal parts. However, if the loop exits before the third pointer reaches the end, it indicates that the binary patterns of the parts are not identical. In this case, it is not possible to divide the array into 3 equal parts, so we return -1, -1 to indicate failure. Here, we start by importing the necessary utilities and defining our solution class. The main method, 3 equal parts, takes an integer array as input. The first step is to count the total number of ones in the array using a simple loop. If the total number of ones is not divisible by 3, it is impossible to divide the array into 3 equal parts, so we return -1, -1. Similarly, if there are number ones in the array, the entire array can be divided into any 3 parts, and we return 0, our length 1, as an example. Next, we calculate how many ones should be in each part, which is given by total ones divided by 3. To prepare for the next step, we initialize variables to store the starting indices of the 3 parts, first, second, and third, and set up a counter to track the number of ones as we iterate through the array. Now, we loop through the array to determine the starting indices of the 3 parts. Each time we encounter a 1, we increment the count. The first 1 marks the start of the first part, so we record its index in the variable first. When the count reaches the number of ones for the second part, we record the index in second. Similarly, the index for the beginning of the third part is recorded when the count matches twice the number of ones per part plus 1. After identifying these indices, we verify whether the 3 parts have the same bit pattern. Using a while loop, we compare the corresponding bits of the 3 segments, advancing through the array as long as they match. If we successfully reach the end of the array, it confirms that the 3 parts are identical, and we return the indices marking the end of the first part and the start of the second part. If the while loop fails before reaching the end of the array, it means the 3 parts do not share the same bit pattern. In this case, it is not possible to divide the array into 3 equal parts with the required properties, so we return -1, -1. This simple yet efficient implementation ensures that we only perform the necessary checks and computations, making it suitable for larger input arrays as well. Here, we start by analyzing the example array 1, 0, 1, 0, 1. First, we count the total number of 1s in the array, which gives us total _1s equals 3. Since the total number of 1s is divisible by 3, we can proceed to divide the array into 3 equal parts. Each part must contain exactly ones underscore per underscore part equals total underscore ones // 3 equals 1 1. Next, we identify the starting indices of the 1s for each part. As we iterate through the array, we count the 1s and assign the indices where the count reaches 1, 2, and 3, respectively. So, the first one is at index 0, the second one is at index 2, and the third one is at index 4. With these starting indices, we now compare the bit patterns from these positions to ensure all 3 parts are identical. By comparing ARR first, ARR second, and ARR third, and incrementing these pointers, we confirm that the patterns match. For example, at first equals 0, second equals 2, and third equals 4, all values are the same. We continue incrementing until we reach the end of the array. Since the process is completed successfully and third reaches the array's end, we can determine the result as first 1, second, which equals 0, 3, for this example. Now, let's look at the next example, where the array is 1, 1, 0, 1, 1. First, we count the total number of 1s, which is total underscore ones equals 4. Since 4 is not divisible by 3, it is impossible to divide the array into 3 equal parts with the same number of 1s. Therefore, the result here is -1 - 1. Finally, we examine the array 0, 0, 0, 0. Counting the 1s gives us total underscore ones equals 0. If there are no 1s in the array, the problem simplifies. We can return 0 len ARR 1, which in this case is 0, 3. These examples demonstrate how the solution handles different cases systematically, ensuring correctness for both valid and invalid scenarios. The time complexity of the solution is determined by 3 primary operations. First, we calculate the total number of ones in the array using the sum ARR operation. This requires iterating through the entire array once, which contributes n to the overall complexity, where n is the length of the array. Next, we identify the starting indices of each part, which involves another pass through the array using a for loop. This operation also contributes n. Finally, the algorithm compares the binary patterns starting at these indices to ensure they match. This pattern matching step, implemented using a while loop, may also require iterating through the remaining elements of the array, adding another n. Since these 3 operations occur sequentially, the total time complexity is the sum of these components. n from counting the ones, n from determining the starting indices, and n from pattern matching add up to a total time complexity of n. Now, moving to the space complexity, the algorithm is designed to work in place without creating additional copies of the input array. This means only 1 extra space is used for storage. Additionally, a fixed number of auxiliary variables, such as integers for counting and indexing, contribute to a constant space requirement. Since no data structures or memory proportional to the input size are utilized, the overall space complexity is 1. This makes the solution both time efficient and memory efficient. Analyzing the best, average, and worst cases, we observe that in the best case scenario, when the total number of ones is not divisible by 3, the algorithm terminates immediately after calculating the sum, resulting in n time. For the average and worst cases, the algorithm performs all 3 steps, counting ones, locating the indices, and pattern matching, each taking n time. This means that regardless of the input distribution, the algorithm consistently exhibits linear behavior. As a result, the average and worst case time complexities are also n, making the performance predictable. When comparing the optimized approach to a naive solution, the benefits become clear. A brute force method would involve trying all possible ways to divide the array into 3 parts and then checking if the binary values of these parts match. This would require iterating through all possible pairs of indices, resulting in a time complexity of n cubed. In contrast, the optimized approach leverages the properties of the binary array, focusing only on the positions of the ones to directly identify the valid partitions. This strategy reduces the problem to just 3 linear passes over the array, achieving a much more efficient n time complexity. Finally, let's confirm the mathematical reasoning behind the big O complexity. The sum ARR operation, which calculates the total number of ones, iterates through the array once, giving us n. The for loop used to locate the starting indices of the three parts also requires a single pass, contributing another O(n). The while loop for matching patterns, even in the worst case, involves only scanning the remaining portion of the array, adding at most O(n). Combining these steps, the overall time complexity remains O(n). Additionally, since the algorithm uses only a fixed number of variables and does not allocate extra space based on the input size, the space complexity is O(1), confirming that the solution is both time and space optimal. When working on this problem, it's important to be mindful of some common mistakes that can trip you up. One major oversight is ignoring edge cases, such as arrays that are too small to be divided into three parts. If the array has fewer than 3 elements, splitting it into 3 segments isn't possible, and failing to check for this can lead to errors like index out of bounds or invalid results. Another frequent issue is incorrect segment identification. For example, if you misinterpret the indices and use overlapping ranges or leave gaps between segments, the validation process will fail since the segments won't represent equal values. Additionally, be cautious about comparing binary values directly as strings. This can go wrong because binary strings might have leading zeros, which can make comparisons unreliable unless properly converted to integers. Lastly, avoid brute force implementations that iterate through all possible pairs of indices, I, j, without eliminating invalid options early. This approach results in a time complexity of O(n cubed, which is impractical for larger arrays and will likely time out in competitive programming scenarios. To optimize your solution and avoid inefficiencies, using prefix sums is a highly effective strategy. A common mistake is failing to leverage these cumulative sums, which allow for quick calculation of segment values without needing to recompute sums repeatedly. Recalculation increases the time complexity unnecessarily, so prefix sums can make your approach much more efficient. From an interview perspective, this problem is a great test of your ability to recognize patterns. It's a variant of the classic subarray sum problems, and interviewers may look for your ability to optimize brute force solutions using techniques like prefix sums or hash maps. You should also focus on how to reduce the complexity from O(n cubed to O(n squared, or even O(n), depending on the approach. Be ready to discuss how you handle edge cases, such as empty arrays, arrays that are too small, or arrays with repetitive values, as this demonstrates robustness. Additionally, if you evaluate multiple approaches, explain the trade-offs between them. For instance, you might choose one method over another because it's more efficient or simpler to implement given the constraints. This problem is closely related to several others, and drawing connections can help deepen your understanding. For example, LeetCode problem 560, subarray sum equals k, involves finding subarrays with a specific sum, and prefix sums play a key role there as well. Similarly, LeetCode problem 930, binary subarrays with sum, deals with counting binary subarrays that sum to a given value, which is conceptually similar to the binary handling in this problem. Another related problem is LeetCode 1248, count number of nice subarrays, which also uses prefix sums but focuses on subarrays with specific properties. Finally, LeetCode 1013, partition array into 3 parts with equal sum, is directly related and involves splitting an array into 3 equal sum parts, though it's slightly different in that it doesn't involve binary values. Understanding these related problems can provide valuable insights and help you recognize recurring patterns in array and prefix sum problems. There are several alternative approaches you can consider for solving this problem, each with its own trade-offs. Using prefix sum optimization is a popular choice because it avoids recalculating sums repeatedly. While this method does require additional space to store cumulative sums, it significantly reduces redundant computations, bringing the complexity down to O(n squared, or even O(n) in certain cases. Another approach is the sliding window technique, which is useful when there are constraints on segment lengths. However, this method may not work as effectively if the segments vary widely in size, so it's best used in specific scenarios. Finally, you can use a hash map to store values for quick lookups of target sums. This approach is particularly efficient, with a time complexity of O(n), but it does come with the trade-off of additional space overhead proportional to the array size. Each of these methods has its strengths and weaknesses, and the choice often depends on the constraints and requirements of a given problem. Great job! We've successfully reviewed the 3 equal parts problem, discussed its constraints, and compared different approaches. Remember the key takeaways: focus on breaking problems into smaller steps and always evaluate the efficiency of your solutions. Thank you for joining, and don't forget to like, share, and subscribe for more content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!